Welcome back. In this submodule, we're going to discuss two very interesting but challenging concepts in advanced trigonometry. We'll discuss the law of sines first, and then the law of cosines. These are among my favorite topics in trigonometry because they really extend the power of the tools we have. What are the limitations of what we've seen so far? Well, our trigonometric functions have so far been limited to right triangles. So they are powerful tools. However, if you don't have a right triangle, there's nothing you can do so far. This law of sines and cosines helps us solve this by giving us tools for triangles that are not right triangles. They provide relationships between the sides and angles of a generic triangle, by which I mean one in which we don't assume there's a right angle. Any triangle is amenable to these techniques. So first, let's look at law of sines. If you open up a textbook, you'll typically see it written as follows. Now, in order to interpret this, we need to have a particular triangle in mind. So let me draw a picture. So here's a generic triangle. None of the angles are going to be assumed to be right angles. I'll call the angles A, B, and C. What the law of sines tells me is that the relationship between the ratios of the angles A, B, and C, capital A, B, and C, are related to the corresponding side lengths in a very natural way. That the ratios of the side length to sine of that angle is constant. So sine of A, big A, or rather little a divided by sine of big A is equal to little b divided by sine of big B, which is equal to little c divided by sine of big C. So why is this useful? Well, what it tells me is that once I know the three angles on the inside, which really requires me only to know two, since the third is automatically determined, and one side length, I automatically know all the sides of the triangle, because the ratio between angles and side lengths is constant. So if I know one of those ratios, that is, I know one angle on one side, then I can use the angles on the inside to compute the other two side lengths. So for example, let's look at a specific triangle. Let's say that this was 100, 40, and 40. So not a right triangle, but suppose I knew that this side length was 5, and I wanted to know this side length here, opposite to 100. I can use the law of sines to do this, because I know that x divided by sine of 100 is equal to 5 divided by sine of 40. So solving for x is equal to sine of 100 divided by sine of 40 times 5. So this is the power of law of sines. Once I know all the angles, I can compute all of the side lengths just given one of them. Now, law of cosines is a bit more complicated looking, but I think it has an easier intuition. I'll try to convince you that it's a generalized Pythagorean theorem. So let's take a look at law of cosines. Again, it's written in this way, so if you open up a textbook, you'll typically see something like this. But I need a particular triangle in mind in order for it to have any sense. So here will be the angle theta, and I'll let C be the length of the side opposite theta, and A and B the other sides. So law of cosines tells me that C squared is equal to A squared plus B squared, but minus something, minus 2AB times cosine theta. So let's put this in context. I want to compare this to the Pythagorean theorem. So let's recall what the Pythagorean theorem PT says. says that if I have a right triangle, then the hypotenuse, or the side opposite the right angle, has the property that its side length squared, c squared, is equal to a squared plus b squared. So this assumes c is opposite a right angle. Now, in the case of the law of cosines, we make no such limiting assumption. So here I'm allowing the angle in question to be perhaps larger than 90 degrees, maybe smaller also. So here I say that a squared plus b squared minus 2ab cosine of theta equals c squared. Now, you can maybe perhaps see the similarity now, but it's actually even more similar if we notice that the law of cosines includes the Pythagorean theorem as a special case. That is, when theta is equal to pi over 2, the law of cosines is exactly the Pythagorean theorem, right? So if theta equals pi over 2, i.e. a right angle, then what does this look like? A squared plus b squared minus 2ab cosine pi over 2 equals c squared. And we just have to notice one thing, which is, what is cosine of pi over 2? It's 0. So this whole term goes away. And I just get a squared plus b squared equals c squared, i.e. the Pythagorean theorem. So I think this is remarkable. What the law of cosines is really telling us is the Pythagorean theorem can be generalized to any triangle. What cost do I pay for this generalization? Well, I pay for this minus 2ab cosine of theta. I find this type of idea to be useful in my research, in Fourier analysis, for example, and in general mathematical analysis. For us, we mainly want to be able to compute with it. You should be able to use the law of cosines to find the missing side length of a triangle, knowing the other two side lengths and the interior angles. So if you don't understand it at this point, I understand that. This is a tricky concept. I recommend working on the questions I've assigned and consider spending some time with the readings I've assigned, as I think that they will really help you cement your understanding of this idea.